Before we get started with this month's lesson, I'd like to introduce a friend of mine who's going to help us out. This is Harvey. Say hi to the students. They're over there. Come on, Harvey. We've been through this before. Yes, they can see it. I know you can't see them, but they can see us. All right, here we go. So this is Harvey. If you've seen the old Math Counts minis, you've seen Harvey in action before. You know I bring him out here for these geometry problems because he has a very special talent. He has a gift for seeing things that aren't there. Let's start with this first problem. We've got a square and a circle, and they intersect so that each side of the square includes a chord of the circle that's equal in length to the radius of the circle. And we want to find the ratio of the area of the square to the area of the circle. So all we have here to start with is a square and a circle. What? And an equilateral triangle? Where connect the center of the circle, all right, to the endpoints of a chord. Well, I guess that's a smart thing to do. You got a chord in a problem, connect it endpoints to the center of the circle. That is an equilateral triangle. My man's crazy smart. I tell you what, we're told that this chord is equal in length to the radius of the circle. So this chord is equal in length to this and to this, so this is an equilateral triangle. How does that help? Oh, that's right. Yeah, I should have thought of that. Got an equilateral triangle, you draw altitude of the equilateral triangle, and that splits the equilateral triangle into two 30, 60, 90 triangles, because that's a 60-degree angle, because the triangle is equilateral, and then this altitude, that gives us a 90-degree angle, so that's a 30-degree angle. And this side length, the side length of the equilateral triangle, of course, is r. You go opposite the 30-degree angle, you have a side of length r over 2, and because it's a 30, 60, 90 triangle, the long leg of the triangle is square root of 3 times the shorter leg. So this long leg is r times the square root of 3 over 2. And this long leg is half the side length of the square. So the square has side length double this, which is r times the square root of 3. So the area of the square, we square r times the square root of 3, and we get 3r squared. Of course, the area of the circle, that's pretty easy. That's just pi r squared. We cancel out the r squareds, and we get our ratio. 3 over pi. Yes! All right, on to the second problem, Harvey. Oh, boy. Yeah, that's a lot of words. A lot of words here. So we start with all these words. The way we turn words into math in a geometry problem, we draw the picture. So we're going to draw the picture here. We're going to start with rectangle A, B, C, D, and point E is on side CD such that the area of triangle ADE is 1/5 of the area of the quadrilateral ABCE. So E is going to be pretty far over here, I think. Maybe call it right there. We'll call this E, and we'll go ahead and build that triangle. And we're told that this triangle is 1/5 the area of this quadrilateral out here. So how are we going to relate this one triangle to that two triangles? Where are two triangles? Draw the altitude from E to AB, and we make another right triangle. This triangle is congruent to that triangle. This is really smart. This triangle is congruent to this triangle, so they have the same area. So if we call this area X, then this area also is X, because these two triangles are identical. Well, if this area is X, then this quadrilateral has area 5X, because we're told that ADE is 1/5 ABCE. So this quadrilateral out here is 5X, which means the rectangle is 4X. So now we want the ratio of the length of segment DE to the length of DC. DE to DC, and that ratio is going to be equal to the ratio of this rectangle to the large rectangle, because their heights here are the same, so their widths here, the ratio of their widths is going to be the ratio of their areas. So we're going to have DE to DC, area here is 2x, and the area here is 6x. 2x to 6x, and that, of course, simplifies as 1/3. Yeah, right there. All right, last problem, Harvey. We got this. Oh yeah, that's way too many words. This is too many words for a geometry problem. Too many words for any problem, maybe. All right, here we go, Harvey. I'll draw the diagram. You solve the problem. All right, or you solve the problem. That'd be even better. So we're going to start with, let's see here, segment. Draw a diagram large because it's a long problem, so it's probably a complicated diagram. We start with segment FG. M is the midpoint of the segment. We'll call it right there. And A and B are on here so that FMA and MGB are equilateral. So I'm going to draw two equilateral triangles. And there we go. I've got two equilateral triangles. Three equilateral triangles. He says three. I only see two. How many do you see? Yeah, I only see two. Got two equilateral triangles here. And then we want to draw FB and GA. All right, FB and GA. And they intersect at a point K. And we have to find this angle right there, GKB. So we start off with a midpoint, and then with two equilateral triangles. Yes, Harvey, two equilateral triangles. It says right there, two equilateral triangles, not three. Two equilateral triangles, and then we draw these two lines, and we've just got a whole big mess here. Draw AB. Okay, I'll draw AB. Harvey tells me to draw AB. I draw AB. Now I'm going to draw what Harvey sees. That's three equilateral triangles. He's right. ABM is equilateral as well. Because M is the midpoint of FG here, MG equals FM, and that means all the sides of this triangle have the same length as all the sides of this triangle. So BM and AM have the same length. This angle is 60 and this angle is 60 because these two out here are equilateral triangles. So this has to be 60 as well because this is a line and these three have to add to 180. AM and MB are equal. They have a 60-degree angle between them. That means this is an equilateral triangle, and we like equilateral triangles because we understand them. Now, how does that help us with this? Well, that means that, what? Oh, yeah. Rhombus. That's right. ABGM is a rhombus. All these sides are equal. AB equals BG equals GM equals MA. It's a rhombus. Its diagonals are perpendicular, even though they don't look perpendicular. I mean, I know Harvey sees perpendicular lines here. I sure don't, but that's only because I don't draw very well. But we know that this is a rhombus, so these diagonals are perpendicular. Similarly, BF and AM are perpendicular. These lines are altitudes of this equilateral triangle. K is the center of this equilateral triangle. So if we draw this here as well, when we draw that, when we connect the center off to each of these vertices, we draw these altitudes. That means this is a 30, 60, 90 triangle right in here. Because K is the center of the equilateral triangle, BK bisects this angle. These two angles here are equal. So this is 30 degrees. This is an altitude of this triangle. This is 90 degrees. And that means the measure of GKB is 60 degrees. And we're done. Nice work, Harvey. Making these Math Counts videos is hard work. I could use some help. I could use your help. Go grab your video camera, Math Counts handbook, some friends, make a math video, upload it here at realmath.org. We're going to take some of the best ones, and if yours is one of those, we're going to give you a trip to Orlando.